Welcome to this week's Geometry and Topology seminar at Durham. It's a pleasure to have Rhiannon Dougall, who just recently joined the department, and she's going to talk about co-amenability of a subgroup is characterized by its growth when in the presence of hyperbolicity. Thank you, Rhiannon.
Thanks. Yeah, thanks for the opportunity to talk to you. So it's always good to be able to tell you about the problems I work on and also about the kind of tools that I use. Not to sort of self-promote myself, but I'm giving a colloquium in about a month's time. So don't worry, there's not going to be too much overlap with, well, there will be some amount of overlap. There's a sort of theme of what I work on. But I decided to have a more narrow focus into the geometry part of what I've been doing. So today, so the goal of this talk today is to tell you what this problem is that has this long title. And a side aim is to tell you a little of the ergodic theory of isometric groups acting on, and I wanted to say Gromov hyperbolic spaces, but that would be a lie because in this talk, I won't actually work in the category of Gromov hyperbolic spaces. I'll be working with something slightly nicer. Really, it would apply to cat-1 spaces, but that's also a lie because I'm not ever going to define what that is. So it's going to be a bit about the ergodic theory of isometry groups acting on big negatively curved Riemannian manifolds. So things like the upper half plane, but more general than that. So as I said, this is a side aim to tell you a bit about my tools. Okay, so let's begin with what it means to be amenable or non-amenable, because this is something that's quite nice from a mathematical viewpoint. You can give nice public talks on the Banach-Tarski paradox. I am going to just go into the definition of amenability that I use in a second, but let me just draw a cartoon. What does the Banach-Tarski paradox tell me? Roughly is if I have an orange, this is a picture of an orange, I can decompose it into some pieces. And then with these pieces, I use some isometries in R3 to move them around. And what I'll produce two oranges of the same size. So of course, this is impossible with actual oranges and any reasonable notion of cutting it up. So these pieces that I've broken orange into in particular, they must be non-measurable. But what's happening is that inside the isometry group of R3, there's a non-amenable group. So let's have an actual definition. All my groups in this talk are always countable, finitely generated groups. I mean, the finite generator is not too important actually, but in particular, they're always countable. There are no continuous groups that I think of anyway. So a Banach mean on a countable group is a linear functional, a mean on the set of bounded sequences so that it's finitely additive. It's G invariant. So if I took one of these sequences in the group and I translated it using the permutation of the group acting on itself, I'd get the same mean. So the mean is translation invariant. And a reasonable property of a mean, I suppose these functions should have been non-negative, and well, no, maybe that's fine actually. No, that was fine. Reasonable property of a mean is that it should not exceed the supremum of f and also should be bounded below by the infimum of f. So we say that G is amenable if there exists a Banach mean. And so in this picture on the left, there's not a Banach mean in this case because I started off with something of one size and I turned it into something twice that size. So size was not preserved on the left. And just to note, the Banach mean, I only ask it to be finitely additive because if it was countably additive, then it would have to actually be a measure. And well, you just can't have a countably additive mean, but you could have a finitely additive mean. I found this definition quite hard. So actually, I much prefer a combinatorial definition, and I much more use a combinatorial definition. So which is due to Filner. It's an equivalent way of stating amenability for a countable group. It's for all epsilon, and for any finite set in the group that I take, you can think generators, any finite set. I can find another finite set that is not moved very much under the action of S. So in a picture, I think the S is a set of directions in which I'm moving. My finite set is what's in black. And so it doesn't move very much if the symmetric difference is small. And I'm sure you can all negate what that means, but I just also want to say, so G is non-amenable if in particular there is some number and there is some set, so that any other finite set is moved at least that much in by some direction. Yeah, so I think about non-amenability more maybe. So finite sets in particular, maybe think of those as being indicator functions. So I could extend this from indicator functions to little L2 of G. So it's nice to rephrase this in terms of the left regular unitary representation. So that is a representation of G as unitary operators in little L2 of G. And all it's doing is taking a function, instead of evaluating at X, evaluating at f of G inverse of X. So, and so now what might I define? So just to generalize what I was saying about moving a set a definite amount, given any unitary representation, I might want to define this quantity, sometimes called a Kesten constant. This S was meaning for it to be a, let's just check my pen. Yep, so this S here, think of this as being a generating set. Let's say it's a generating set. So this just extends from from finite sets or indicator functions to all of some Hilbert space. This Kesten constant is by how much can you move a vector? And so G is amenable precisely when this Kesten constant is 0. So when there are always sets that you can't move very much. And okay, some point to make is amenability. I've phrased it here in a very combinatorial way. It can be enlightening to think of it in terms of unitary representations. I don't think I'm not really going to convince you very strongly of that today, but one example we'll think about is if I have a sequence of quotients of some groups. And so we'll see that later as a way why it's useful to have unitary representations. But maybe also just to point out, since I've mentioned these Kesten constants here, a related definition is if this number was bounded away from 0 for all unitary representations of a group that don't have a fixed vector, that would be called property T. And that's like quite a strong property used in rigidity, but this is a particular baby step on the way there. Okay. Well, let's have some examples. So the integers are amenable. How do you see this? So you have your set of directions S, and you just choose F, your finite set, to be really large in terms of those directions. So even though you think S is translating by a lot, you just choose F really large, and then it's not moved very much. And in general, also any group with sub-exponential growth. Yep, any group with sub-exponential growth is amenable, so the integers fell into that. Examples are non-amenable. The free group on K generators is non-amenable. Let's just recall what that is. That is, it's got K elements along with their inverses, k elements along with their inverses that generate the group, and it's a collection of what we call reduced words. So you write a word in that set, and you just make sure not to put something and its inverse next to each other. So this is a picture. So the empty word, you've got the word A, AB, or AB inverse. It's nice, something maybe Gromov realized is that it's useful to turn a group into a metric space. So in particular, if we turn this group into its Cayley graph, here, this was the identity, this is A, this is AB. And so it's not the geometry of the integers, because AB, A inverse is not going to join up with taking the other route. And so this is the metric space, and you imagine, well, you define every edge to have length 1, and you just put a copy of the interval in there to turn it into a connected, complete metric space. And in particular, this is a tree. Good. So hopefully you know these things already, but always nice to recall the pictures. And okay, the free group, you can see that it doesn't have a Banach mean by a paradoxical decomposition. And instead, I'm going to touch on a different way of showing that it's non-amenable, but just to say, if you're interested in the notion of paradoxical decompositions, it's misspelled, then this is the go-to example. And right, so now any group that contains a free group will also be non-amenable. And to point out, the free group has exponential growth, so strict bigger than 0 here. So these are, so, okay, yeah, so as I was saying, a free group has strict exponential growth. So these examples have strict exponential growth. But it's not equivalent. There are amenable groups over here that do have exponential growth. The lamplighter group is an example of something with exponential growth that's still amenable. So it's not just, it can't be phrased just in terms of the growth of words. Okay, so motivated by that previous page where I gave you an example of amenable groups that contain free groups, there was a question a while ago, might have been by von Neumann, whether every non-amenable group had to contain a free group. So those were the initial examples. So Grigorchuk's criterion is a particular way of checking that. So recall any finitely generated group G can be expressed as something in terms of relations, or in other words, it's a quotient of a free group. As I already said, the free group has exponential growth that you can compute. So this here is the number of elements of the free group whose word length is n. So you write G as S1 up to Sn in reduced form. So the growth is log 2k minus 1. It's useful to think about what's the growth of a normal subgroup relative to the generating set for the free group. So that is, I count, instead of counting all elements in in the free group, I'll count elements of the normal subgroup instead. So of course, this number on the right is smaller than the number on the left. And in a picture, that is, the points in red are the elements of the normal subgroup. So it's a smaller subset to count. And so Grigorchuk and Cohen realized you could understand amenability as you want to characterize amenability of G in terms of somehow the growth of the free group modded out by the growth of this normal subgroup. So to state that precisely, for any normal subgroup, we have that the quotient is amenable if and only if the growth rate of the normal subgroup is as large as it can be. It's sort of a fairly natural thing to imagine that it's saying you have to have lots and lots of relations in order to be amenable. And amenability is sort of meaning small. Right, so that was a way to check that there do exist non-amenable groups that don't contain free groups, particular Burnside groups where they're torsion groups, they can't contain a free group, and where you could really compute what the growth of this normal subgroup is, what the growth of the relations is. So it was useful in that case. And there was also a conjecture, it was also conjectured by Grigorchuk that it shouldn't just hold for the free group. You should be able to replace the free group by other negatively curved groups. I'll say what it means at some point. And that if I had a word hyperbolic group and I took a normal subgroup of it, then the growth where I replace in this formula, where I replace the free group with gamma naught, and I replace the normal subgroup with gamma, that I should be able to have that same criterion that I characterize amenability of a quotient in terms of relative growth of the normal subgroup. And to say, why only word hyperbolic groups am I asking for here? For example, if I have a direct product of two free groups, then I can find a normal subgroup which would violate this property. So that would be a quotient which is non-amenable but has the same growth rate. And in the other direction, I can find an example where you have the same growth rate, but where you have different growth rates, but you are amenable. So actually, the Lamplighter group could give you an example for that. So it can't be a completely naive proof, because it can't hold for every group. And why I don't know why you would believe this conjecture, other than the sort of general philosophy that word hyperbolic groups should behave like random, or something we see in hyperbolic dynamics is that you expect dynamical quantities to behave like random. And I'm going to try and explain to you that, well, a lot of time has passed already, that it's too hard to try and work with the increments of what's happening. So our proof is a way of avoiding, of waiting until what happens at infinity in order to deduce the conclusion. But I mean, it's hard to compare with random walks. That's what I'm trying to say. Okay, and let me tell you what it means to be amenable again in terms of random walks, and that's sort of a way to believe the Grigorchuk criterion. So a random walk in a picture, you have G, you multiply by S1 or S2 with probability corresponding to that generator. So for example, the uniform probability on the generating the free basis of the free group, the probability to return in n steps, this k should be an n here. So that is, you count the number of products so that they evaluate to be the identity. And the probability of each product is 4 to the minus n. So the likelihood of returning to the identity corresponds to the likelihood of a product being trivial. So this was a picture to say that it's quite hard to be a trivial element. In fact, you have to backtrack. So this was the only way to come back to the identity in the free group is to backtrack along exactly where you went. And that's because of its geometry being a tree. And then if you wanted to understand normal subgroups, you can have the random walk on the normal subgroup, where now you're asking whether or not your product landed in an element of the normal subgroup. And you can also rephrase this in terms of the random walk operator which I'm not going to say very much about actually. So it's an equivalent criterion by Kesten, which is that G is amenable if and only if the random walk operator has spectral radius equal to 1. I didn't say the probability should actually generate G. And symmetry plays a role here, because if the probability is symmetric, then the operator you have is self-adjoint, and so you can actually figure out what its spectral radius is, and it turns out to be given in terms of returns to the identity. This is the radius of convergence of the random walk. So what we learned in this slide is that there was an operator approach, spectrum of an operator, to tell us about amenability. And on the previous slide, I was telling you that we were interested in relating relative growth to amenability of the quotient. Just to say that you can use some approach based on random walks to show that the quotient being amenable will imply equality of growth rates. And this was sort of considered the easy direction for a while. So I'm really not going to say very much about this. So what you should think in the rest of the talk is I'm always asking whether the growth of the subgroup attaining its maximal value will imply amenability. So I'm always going to be thinking about the other direction. So I need to tell you what a Gromov hyperbolic space is, because I want to touch on the ergodic theory of them. So following Gromov, so I start with a proper geodesic metric space. That means that it's locally compact, proper locally compact, and between any 2 points there exists a geodesic. And I say it's delta hyperbolic if the triangles in X are delta thin. And the way to define this is just to draw a picture really, which is I have a point X and a point Y and a point Z. And I surround the segment XY with a delta ball, surround the segment YZ with a delta ball. And then I notice that the segment XZ is just contained in this case, but is completely contained inside that union. And so then for a group to be word hyperbolic, you apply this definition to its Cayley graph. And so its Cayley graph, the geodesics are going to be segments, edge segments. Triangles might look like this. For the free group, it was really a tripod that was the triangle, and so it was zero hyperbolic. But in general, in a word hyperbolic group, it need not be a tree. You could have some small cycle going on here. So examples of the free group I've mentioned is word hyperbolic because it's a tree. Yes, so it's important to stress that in this definition, it turns out that it's independent of the property of being word hyperbolic turns out to be independent of the generating set. So any Cayley graph I took, there might be different deltas, but it turns out that you'll be delta hyperbolic, your word hyperbolic if one and every generating set will give you some delta for which you're delta hyperbolic. So that's important to point out. And sort of related to this notion of, because G acts on its Cayley graph, related a group that acts co-compactly on a, well, Gromov hyperbolic metric space will also be word hyperbolic. Uniform lattices in SL2R coming from a different side of things. These are also word hyperbolic. Yeah, so the main examples of Gromov hyperbolic spaces that I'll really think about is simply connected, complete, negatively curved Riemannian manifolds. Although I would like to give you the exposition for Gromov hyperbolic spaces. And here is a fact. A non-elementary word hyperbolic group is non-amenable. And to verify that, you find out that it contains a free group. So the gamma naught that I mentioned oh no, the gamma naught that I mentioned is itself non-amenable, and I'm looking to see if I can characterize when its quotients are non-amenable or amenable. And to tell you a little bit more about the geometry, so this is what we're going to understand this fact a little bit better by the visual boundary. The visual boundary is a collection of rays starting from some point modulo some equivalence relation. That is, I have two rays starting at some point in X. That's what that means. I will say that they're equivalent if they stay a bounded distance for all time. So an example is, right, so I have just finished the definition of the visual boundary. An example of the visual boundary is you take the hyperbolic plane or the Poincare disk, and if you know the construction, you know that there's a boundary that seems to be there. And in fact, this coincides with the visual boundary. If M, I think this is actually X, what I wanted to say. If X is a complete simply connected Riemannian manifold of negative sectional curvatures, in particular, it's one of these Gromov hyperbolic spaces, you can identify this is not quite right. What I meant to say is a sphere in the tangent space at a point, space of directions at a point with the boundary, with the visual boundary. Nevertheless, you do want to think that the visual boundary is describing what's happening at infinity. So although you could think of it as locally as directions, I want you to think of it as what happens at infinity. And so Cayley graphs are problematic because geodesic rays are not unique in their equivalence class. I can really have two of these, this ray gamma 1 and gamma 2, that are not the same but are equivalent, whereas that doesn't happen in particular in a cat -1 case, but I'm not going to say what that is. Right, so if you know the hyperbolic plane and the Poincare disk, you maybe already know the action on the boundary. And if I had G acting on its Cayley graph, then when I look at its action on the boundary, these are acting by loxodromic elements. So here's a picture. So this is a picture of the Cayley graph with its boundary. So here you have a sequence of points going to the boundary. If I have loxodromic elements with disjoint axes, then I can do a ping pong argument that will find a free group inside my group. So this is a use already for the visual boundary, is telling you about subgroups that you have in your group. Okay, so I've really skipped over what the topology of the boundary is and what the metric is and so on, but at least maybe I have a picture of it. Okay, and so now I was repeating things that you already know. But because I study ergodic theory, I want you to think about in a different way. So I'd already told you Cayley graphs are problematic. So I'm really thinking of this Riemannian setting. So here's the Rhiannon picture. So I can extend my discussion to infinite geodesics. I don't need to have something based at a point. I just want to have two infinite geodesics in my Riemannian manifold X. And the fact is, if you have strictly negative sectional curvatures, then these two geodesics, if they were to stay a bounded distance, then the only possibility is they were actually the same geodesic, but perhaps with a time shift. So it could be gamma 1 of 0 is here and gamma 2 of 0 is here. Once I'm no longer in the rays case, I'm just thinking of an infinite geodesic. So it's better now if you think about the double boundary minus the diagonal. So you take psi and eta. Here's eta. Well, I won't draw it in that picture because that was sort of the false picture. So you have so what you see is the double boundary minus the diagonal. That describes exactly what the geodesics are. And then you can recover what the geodesic flow is. So if the double boundary is the space of geodesics, you just need to choose a time coordinate in order to know where you are on the geodesic. And so you can recover the geodesic flow by taking the double boundary without the diagonal times the real numbers. So this is the geodesic flow on this really big space, but really I want to know about quotient spaces. You might want to know about a quotient manifold. So then the geodesic flow associated to some quotient is simply, now you're going to take this space and you're going to quotient it out by the group action. I haven't told you how the group acts on the real coordinate yet, but there's a formula to describe that. So yes, so this is a useful viewpoint to have in mind. And so I use this viewpoint. I'm not thinking so much about the Riemannian metric anymore. I've left that behind. And so I can use this viewpoint to think about measures that are invariant under the geodesic flow because I can describe them. I describe them in terms of measures on this space. So I ask for measures that live on this space that have, well, not quite invariant. So if the measure on this space that's invariant under the action of the group, or a measure on this space that transforms in a nice way under an action of a group. So I'm going to use this machinery in order to solve the problem. It was kind of important to take this detour because this is how we're going to solve the problem, which was quite naive and about growth of a subgroup. Right, hopefully that's an all right picture. So now I tell you what the theorem is. So if I take X as a proper Gromov hyperbolic space, or you can just think of the Riemannian manifold picture, and I have gamma naught is a discrete group of isometries of X. And I'm going to assume that gamma naught acts strongly, positively, recurrently. What is that? In particular, it generalizes being co-compact. I also just have to add in this hypothesis that the critical exponent is non-zero. I didn't tell you what the critical exponent is yet. That is, it's the replacement of word growth. Before, the metric on the Cayley graph was the length of a word in the generating set. Well, the metric on the Cayley graph was defined in terms of the length of a word in the generating set. Now we just say, I have some metric and I look at the displacement of geo to O and count the number inside of all of radius R. And so when I apply that definition to gamma naught in particular, the orbit of gamma naught grows exponentially. And so now what we will show is that if I have a subgroup, then the subgroup is co-amenable in gamma naught if and only if the growth of the subgroup attains the growth of the full group, so the maximal growth it could have. I didn't tell you exactly what it means to be co-amenable, I only told you what it means for the quotient to be non-amenable, so maybe just take that as, just take it as gamma being normal and the quotient being amenable, or apply it to some particular unitary representations that I'll give you in a second. So, okay, I am telling you what they are right now. I introduced this Kazhdan constant earlier. If I apply that to, instead of the left regular representation, I'm going to think of gamma naught acting by permutations on the quotient group. So it's really gamma naught is acting by a left regular representation, but with a big kernel to it. So you can so then we can also describe what could happen to a gap in critical exponents over a collection of subgroups in terms of these Kesten constants. But I really just want to think about actually what's happening in number one, because number one is generalizing that conjecture of Grigorchuk, although I did say that the Cayley graph case was done by Coulon, Dalbo, and Sambuzetti. But their approach was quite particular and involved symbolic coding, and in some ways, so they have a kind of special operator that they can use in their setting. I'll say what about it in the next page, but we wanted to do this in a way that would generalize better for one reason. And now we can have a more relaxed dynamical hypothesis on the action of the group, and it's closer to being optimal now. So anyway, the theorem is we can characterize growth of the subgroup. So we can characterize amenability of the quotient by growth of the subgroup. So I want to tell you a bit about how we do this, but first I should tell you, what am I going to tell you first? First, I will touch upon what it means to be strongly positively recurrent in order to again explain why this kind of theorem is not obvious. So I mentioned the geodesic flow already. It does play some role here. So if you have a manifold, I think I want to draw, the picture has appeared good. If I have some manifold and you imagine there's a negatively curved metric on it, if it's not compact, then the ergodic theory of the geodesic flow is not so good. And I'm not going to really say what a measure of maximal entropy is, but the dynamics might not be so good in this manifold. So you could have quite long excursions into this cusp. So in this picture, the cusp could be a problem. So M is X modded out by the big group gamma naught. And so there's an example of Dalbo, Hotel, and Peignet. So the cusp, it corresponds to a parabolic element acting on X. And so they construct a metric on X, which still satisfies the kind of desirable properties of being pinched and negatively curved, for which the growth of the parabolic subgroup, it's isomorphic to Z, but it's so distorted. The growth is equal to the growth of the whole group. And this is bad. So this is a case where you're not SPR. So this is bad for ergodic theory. So what does it mean to be SPR? SPR is about first return trajectories. So this is a picture where G is a first return. So the green line is a geodesic. G is a first return, but H is not a first return. And K was just some compact set. So we say that gamma naught is SPR if the first return group, well, it's not a group, the first return set has strictly smaller growth. So the parabolic subgroup in this example, the parabolic subgroup is contained, depending on how you choose K, it can be contained in the first return set. So, okay, so why is this a problem? Because in the topology of this manifold, I can find a covering that looks like a free group. But in this covering, I've still got the cusp. I didn't kill the cusp. So in fact, the critical exponent for gamma will be equal to the critical exponent for gamma naught, despite the fact that their quotient is a free group. So I can find the characterization of growth and amenability can fail for these kind of actions. But anyway, we can just think about gamma naught as being co-compact, and it's already interesting enough. Okay, now some pictures of things that are more familiar. This is the upper half plane, and I've started to draw the orbit of PSL2Z. And here is the critical exponent of the parabolic subgroup. You can compute it. In that case, it's a half. So to reassure you, and then the critical exponent of PSL2Z, it's equal to 1. So this problem that I mentioned with the cusp, it only happens in variable negative curvature, or rather when you are not, in particular, not a symmetric space. And if I wanted to study this problem, if I really wanted to know about PSL2Z, I should be using the spectrum of the Laplacian to do this. And I've written what it is, but of course I'm not really an expert in this. And I also just want to tell you that it's good for orbital counting. So PSL2Z has got some very good ergodic properties associated to it. So as I said, it's more classical to study the spectrum of the Laplacian rather than these critical exponents, these growth exponents. And Brooks was interested, I suppose, in this amenability criterion of Kesten. And so Brooks gave an amenability criterion in terms of the bottom of the spectrum of the Laplacian on certain Riemannian manifolds. And so I'm going to state this in the setting of the upper half plane, but I mean, I want to make the point, he wasn't studying the upper half plane exactly. I mean, he was looking at just more general coverings of compact Riemannian manifolds. So stated in this case, it says that the bottom of the spectrum of the covering manifold is equal to 0, which is the bottom of the spectrum of the compact manifold, if and only if the quotient group is amenable. And you can use this, in fact, you can use this to get the answer about critical exponents. But this relationship is special to the symmetric spaces, that you could go from information about the Laplacian to the critical exponent. So so as I say, we've greatly benefited from having an operator spectral value approach. And also in other dynamical settings, I can use a different operator, which I use a lot in my research, but not in this particular problem. So you can use the transfer operator, so related to the fact that you can encode geodesics for instance, you could use it for PSL2Z. You can encode geodesics on PSL2Z by a subshift of finite type. And so there are other situations where you can use a transfer operator to solve the growth question. So starting with Manuel Stadelbauer, who gave a criterion for amenability in terms of this operator, also used by myself. And importantly, Coulon, Dalbo, and Sambuzetti, when they're solving the Cayley graph problem for word hyperbolic groups, they do use a transfer operator approach. So we wanted to generalize this and generalize it in a way that didn't rely on this operator approach. So our proof really has to be a little bit different. Okay, and I'm going to tell you a bit about the proof because it explains my tools. And you can think of applying all of these definitions I give to the hyperbolic plane or the Poincare disk. So there is a certain probability measure that's really useful to us, Patterson-Sullivan probability measure. So this is a picture of my space X, and the black points here, they are orbits under the group gamma naught, say. They're orbit points under the group. And so how you construct the measure, well, how you construct some measures here is an idea, is you construct it to be some weighted Dirac masses. So for every point in the orbit, for every point in the orbit, you put a weight which is proportional to exponential minus s the distance. So it's probably hard to understand why you would have an exponential appearing here, but it is what it is. And so if s is large enough, this series is finite. And so this measure is well defined when s is large enough. So this series here, this will be defined anytime s is bigger than delta of gamma, the critical exponent of gamma. For reasons I'll touch on, you would like that at s, as s tends to gamma, you would like this normalization, you'd like the bottom term to go to infinity. It doesn't always, when gamma is not a particularly good group, that won't happen. So sometimes you will also see the Patterson-Sullivan measure being constructed where you put in some slowly increasing function. So you can always construct Patterson-Sullivan measures because of this way of putting in slowly increasing functions, but they do cause problems later on. So since X union its boundary is compact, that's a key feature of the visual boundary, that it's actually playing the role of a compactification of the space X. You can take weak star accumulation points of these mu S gammas. And remember, I've normalized it, so it's a probability measure. So I can find some accumulation point over some sequence Sj going to delta gamma, and it's a probability measure. So you always have these. And because either without the C, the sum will diverge, or with the C, the sum will diverge, that means that actually the mass that this gives to the interior is 0, because any single point, you think, is being divided out by a large number. So this is really actually a measure on the boundary. And so I said you can think about the Poincare disk. The usual Lebesgue measure on the Poincare disk is a Patterson-Sullivan measure for a co-compact group acting on it. And these measures, they know something about the geometry. So, there's a certain kind of sets called shadow sets, for which their measure is in some way related to a displacement. So what's that? Shadow set is, if I want to understand the displacement between O and GO, then I can find out something from it by the measure of the shadow. I think I'm supposed to finish soon. And also there's an explicit description of the Rhiannon-Dougall derivatives there. When you push forward by G, it's absolutely continuous with respect to mu of gamma, and there's an explicit way of describing the Rhiannon-Dougall derivative. This is a fairly nice function. When I'm only Gromov hyperbolic, there are problems, though. You don't get an exact relationship there. But to be clear, this is only for elements of gamma. And so I can also convert this to a flow invariant measure with a particular normalization. And flow invariant measure is important to do ergodic theory. Okay, so let's see, how will I conclude? So there's a way to construct flow invariant and group invariant measures using these boundaries. Just to say what's the role of ergodic theory in here. So I know if I had equality of critical exponents, I want to deduce that the quotient group is amenable. Well, if I know that I always have Patterson-Sullivan measures, I have Patterson-Sullivan measure for each group. What's it look like? It looks like that. So actually gamma naught is a good group, so I didn't need the C function. So I have these measures. In a way, this measure is sort of weighted to clearly it's supported on the orbit of gamma and not on the orbit of gamma naught. So it prefers returns to gamma. But the issue with comparing these two measures is that although I have this shadow lemma that is the exact same, that I can only do shadows for the smaller group gamma. So the Patterson-Sullivan measure for gamma on its own isn't really good enough to tell me anything. I can't really compare its support with the Patterson-Sullivan measure for gamma naught because of this. So the idea of what we do is that we want to construct a measure for which we can compare the support, but we'll have to work on two copies of the boundary. But that's a very natural thing to think about, because two copies of the boundary, that's the space of geodesics. And so what we're constructing really a flow invariant measure. And we also want it to be flow invariant on the quotient. And so if indeed, I mean, this property alone, this will tell us that the flow invariant measure that we've constructed is proportional to the good flow invariant measure for gamma naught. So that's where ergodic theory comes into it. Ergodicity gives me a uniqueness of the measure M that satisfies certain properties. And so what I haven't told you is, well, okay, now I need to come up with a measure that also encodes the amenability of the quotient group. And I don't really have time to do that, but this is something that we figured out how to do, but maybe there's still room for us to understand our own construction better. But that's what we were able to do, is construct something using a sort of twisted Poincare series that takes into account the unitary representation. Okay, and so I will stop there. So thanks for your attention.